Welcome back. In this lesson, we're going to talk about the one sample t-test. Sometimes you'll hear it called the single sample t-test, and it is similar to a z-test that we talked about in the last video, but now we'll switch to a t-test when we don't know the population standard deviation. So if I go to my chart that I'm creating and I have the z-test, I'm going to put in single sample t-test. Okay, now it's going to be very similar to what we have up here. In fact, I can even copy and paste it and then make some changes, because we have one sample still, and we want to compare our sample to the population still. The population mean, here's where the change comes in. Population mean is known, but population standard deviation, here's the change, is not known. So we have the population's mean, but we don't have the population standard deviation. So because of that, we have to make a transition from our z-test, where we did know both, to a t-test. Now it's a single sample t-test because we just have one sample and we want to compare our sample to some known population value. But again, we don't know the standard deviation. So similar but different. Some things remain the same. Like this is what I was talking about before, where once we have the process down, it's gonna kind of get easier and easier for you in some respects. So we still specify the null and alternative hypotheses. We'll still select the sample and calculate the necessary sample statistics, such as the mean. We're going to determine the probability of our test statistic. So before we determine the probability of z, this time we'll determine the probability of t, and then we'll make that decision regarding whether or not we're going to reject the null or fail to reject the null. So again, just like the z-test, I think if we think about it in a research scenario, that'll make it a little bit easier. Also, once we go through this part, I'm going to take us over to SPSS and go through the process using SPSS. This next 5 or 6 slides takes you through a little bit more of the math. SPSS, it's really all about setting up your data correctly, knowing the correct steps to run it, and then how do you interpret the output. So this is a little more of the behind the scenes work of what's happening there whenever we do make the transition to SPSS. So in this scenario, Dr. Coffey learns the national average for number of hours per week high school students spend on the internet is 6.75 hours. She wants to compare the national weekly average with the students' weekly average in the local high school. So she believes a one sample or single sample t-test is appropriate for this because she does have one sample, so students in her local high school, and their weekly average compared to the national average spent on the internet. So just like before, we're going to set up that null hypothesis. So H sub O, remember, is the symbol for your null hypothesis, and it is saying the mean of the population of her local high school is also equal to 6.75. So in other words, there's no difference between her students and the national average as far as internet hours go. Her alternative hypothesis, so H sub 1, she set it up as the mean of the population of the local high school does not equal 6.75. So we would say, if you remember, that is a non-directional alternative hypothesis. She's not specifying a direction. She's just saying there will be differences. And we know with a non-directional hypothesis, we are going to use a two-tailed test. Now, like I mentioned before, a two-tailed test is the default in SPSS, and it makes it like a more rigorous test, because it is more difficult to find statistical significance when you're using a two-tailed test. So in my opinion, that's usually the best test to use when compared to a one-tailed test. Our level of significance, or our alpha level, we're setting at 0.05, just like before. Her sample size is 10 students. And when she pulled her 10 students, she calculated the sample mean to be 9.90 hours of internet usage per week. So the question here is not so much, is 9.90 hours different from 6.75, because we can look at that and say clearly that's not identical. Clearly there's a difference, but is the difference enough to indicate a statistically significant difference? That's kind of where we're heading. How likely is this sample mean if the null is true? All right, so if you remember back to the z-test, this was the formula we used. We said our sample mean minus the hypothesized mean divided by the standard error. Whenever we calculated the standard error, we knew right here the population standard deviation. But in this situation, we don't know the population standard deviation. So we can't fulfill this part of the formula. See, we're missing this information. So that's problematic in terms of a z-test. So the fix, or the adjustment we use, is to estimate the population standard deviation using the sample standard deviation. And then we'll calculate it an estimated standard error. All right, so instead of this standard error formula, which is what we used before, we're going to make a change and call this the estimated standard error. So what we'll do there is use the standard deviation of our sample, and I just put a little note up here to remember back from earlier in the semester when we were calculating standard deviation. We took the sum of squares, and then we divided by the sample size minus 1. All right, so that's the standard deviation. And we're still going to divide by the square root of our sample size, and that will give us our denominator, or our estimated standard error, since again, we're not able to calculate the standard error of the population. All right. So, because it's a little different, we use a different test statistic, and this time it's going to be t instead of z, it's t. If you look at the formula, it's the same on the top, right? It's still the sample mean minus the hypothesized mean divided by this new estimate of the standard error. And here it is. This estimate is equal to the standard deviation of our sample divided by our sample size, the square root of our sample size. Okay? Now, again, I want you to know what's happening behind the scenes, but we even though you could pretty easily do the test statistic by hand, we are not going to be doing them by hand. We are going to use SPSS starting with this t-test, but I do want you to see the similarities and know what's happening when you click through SPSS. The t-test got its name from William Gossett, who is a statistician with the Guinness Brewery. Your textbook has a pretty interesting explanation about this process, but really he discovered that the sampling distribution of T is actually a family of probability distributions. So the critical values, or what you use to reject or fail to reject the null hypothesis, are different depending on sample size, unlike the z-test, which had set critical values. And we didn't really talk about those. We are going to come back to these set critical values because we are going to talk about confidence intervals. But unlike before, when I've kind of built confidence intervals into the discussion of each statistic or each test statistic that we go through, I'm going to save confidence intervals for a talk all on its own. And so we're going to hold off on that part. So if this little term right here, set critical values, is not incredibly familiar to you, that's why. Okay. So why not the z-table? Why a new table? Again, because we don't know the population standard deviation, we had to estimate it, which we kind of walked through really quickly. So now that standard error, that denominator, is dependent on the standard deviation of that particular sample. Well, variability from sample to sample will reflect sampling variation with respect to the mean and standard deviation. Unlike Z, that only reflected the variation with respect to the sample mean. So what does all that mean? Well, in a nutshell, that means for you, the researcher, you must use a different table to evaluate whether your results are statistically significant. So if you think back to those Z tables, we had one Z table. We had values from 3 all the way to 0 as far as the Z goes. And we know that the negative value, so -3, we're just using the absolute value. So we had all the values needed in the one table. But now, because of that variability due to sample size, because now we're incorporating it into our test statistic, we have to look at a family of tables or a family of distributions. And that means the critical value or the probability values are going to be dependent on your sample size. The way we take sample size into effect is through degrees of freedom. So you'll see degrees of freedom, and we'll use degrees of freedom as we're writing up our results. But degrees of freedom is a value indicating the number of independent pieces of information a sample of observations can provide. There's a further explanation in the text, but the short version is, for a single sample t-test, the degrees of freedom will equal the sample size minus 1. And that degrees of freedom is going to provide us where on the t-tables we need to look to find those critical values and those probability values. So if we go back to Dr. Coffey, she went through our first step, which we've kind of run through. She specified the null hypothesis, the alternative hypothesis, and her alpha level, or her critical value, her cutoff value. Step 2, select the sample and calculate the necessary statistics. So she did that, a sample mean of 9.90, estimated standard error of 1.29, and the t-value equals 2.44. So determine the critical values of t. I encourage you to look up the value in the table in the back of your book and make a decision regarding that null hypothesis. What is the critical value of t? Okay, so before you do that, let me draw here quickly a curve. Let me pull my pen up. Let me draw for you the curve. All right, so if you're thinking, it didn't quite work, did it? Hold on 1 second. All right, there we go. Okay, so if you're thinking about your distribution, and we have our nice normal curve here, we still have a situation where 0's in the middle, all right, and we have our 1, 2, 3 standard deviations, but instead of being Z, this is T. These are T values, not Z values. So a T of 2.44 is going to be 1, 2, maybe right about here. T right about there. And so what the table in the back of the book is going to do is provide for you a critical value of T. And what that means is it's going to say, okay, for this sample size of 10, which would be a degrees of freedom of 9, what value on this T, kind of number line if you want to think of it that way, on this axis, beyond what value of T can we declare statistical significance? Okay, so it might say 2.01 or something like that is your cutoff value. All right. And then anything beyond that, which this would be, because it falls further out in the tail, we could say that we have found statistical significance. So the likelihood she would have found the sample mean she found of this, if the null is true, is so tiny, in fact, it's less than 0.05, that we're going to declare statistical significance. Or she may not have found that. The critical value may not be beyond or in front of 2.44. 2.44 may not be further out into the tail of that critical value. Okay, so what I want you to do is look in the back of your book in the t-table, look it up, find the critical value for our t-value, which is 2.44 under 9 degrees of freedom, right? 9 degrees of freedom, because we had a sample size of 10 minus 1 equals 9. So that's where your degrees of freedom comes from. And figure out, what is that t value? What is that t critical value? And then make a decision based on that value of whether or not you should reject the null. So that being said, let me mention this. When we calculated the z-test, we could get the exact probability of obtaining our sample, assuming the null is exactly true, right? Well, with a t-test, we can't do that by hand. What it's going to do is just what I said. It's going to give you that critical point according to whichever alpha level we choose. So we know our alpha level. So when you're looking back there in the table, we know that alpha level is 0.05. So you're going to look in that part of the table. We know our degrees of freedom is equal to 9. And we're going to see, based on that, what we have here. It's called t critical. What is that t critical value? So that's what you're going to look up. And whatever that t critical value is, you are going to identify that on your chart. So maybe it's like right here, which I think that's going to disappear. Poof. Okay. Maybe it's like right here. And then you're going to see, okay, well, if this is t critical, that is equal to my 0.05 as far as probability goes. Where does my 2.44, how does it compare? My t obtained, or my t calculated, you'll refer to it. So I calculated t to be 2.44. Well, how does it compare to t critical, that cutoff value? Okay, so maybe t critical equals 2.1 or 2.01. Let's just do 2.1, like the example I was drawing before. Well, if that's the case, then it's going to be over here somewhere. So that means because my t is further, this t is further out in the tail, I am going to find statistical significance. Now, this is different than the z-test, because the z-test, we could get the probability. All right? Well, this t critical, that's not a probability, is it? That's like a z-value. That's our test statistic. And so what happens is it's very easy to get confused, because, let me scratch that out for a second. Whatever that, you can think of this as almost having a dual function. So these are t values, but every t value has a corresponding probability. All right? So whatever this t critical is, we'll need to look it up in the back of the book, but the corresponding p-value, oops, running out of room there, the corresponding p-value for the t critical is 0.05. All right, because that's what we said. We said, hey, whenever we're going to run this test, our cutoff value is going to be 0.05. All right. So this axis right here, you can think of it as performing a dual purpose. When we look up the values, it's going to give us t values at certain probabilities. So our t critical at probability 0.05 is whatever it is. Now I just made that up. I don't know if it's really 2.1 or not. But we compare whatever that critical value is to whatever we calculated. All right. So unlike before, we would get the z calculated. Well, we would also get a probability, wouldn't we, when we looked it up? But for the t-test, we're not getting a probability from the book. We're getting the probability, the t-critical at a certain probability. Okay, hope I didn't confuse anyone with that long explanation. But if it's kind of clear as mud at this point, just kind of hang on, because we're going to go through an example with SPSS, and I think that will help a bit. Let me check the rest of these slides. Depending on what we find, we would report the results were significant at the 0.05 level, or they were not significant at the 0.05 level. Now, the last two are about confidence intervals, and like I said earlier, I'm going to save those. So let me stop here, and on the next video, we're going to do a one sample or single sample t-test using SPSS.